Okay, so we've made some progress. The challenge was get some hardware together. Tell me if you can see this browser window.
Yep.
Okay. And I'm going to make it just a little bit shorter so I can get it out from under my Zoom controls. All right. We've upgraded the Propeller, the driver, matrix driver, to support the P2 cube. This is all 6 panels simultaneously. And thank you, Chip, for spending time with me yesterday and optimizing the code to a really amazing result. In the end, now we handle all panels, all 6 panels of 64 by 64. This is my test setup. And that's the panels wired together, a large supply, so I can drive them at full 8 amps each that I'm driving. This is when they aren't driven as a panel set. I'm driving just one panel, and you can see the data just feeds off to the further panels. My connector is down here at this end. You can see it down here. I'm running a P2 Edge Mini. When we fixed the panel and got the timing correctly, now we can address each of the panels correctly. And what you see is, while our connector's at this end, the 0th panel is out at the far end of the chain, the way the data is driven. And so this is numbering the panels. This is making sure I can draw individually in each panel and color each panel individually in the code. So there are routines that do this now. Same thing, based on numbering in the chain, this should be where the panels locate on your cube. This would be the top panel, the bottom panel. And then I just nominated these as those because it's a cube, rotate it any way you want, but that should be how the thing looks. And then what I did is, what happens if we try and scroll text around the sides of the cube? And so I threw a scroller on there real quick. Now, the scrolling code in my driver is just an extremely rough draft. It's not performant in any way. And it's even worse on a large cube like this, on a large set of panels. This is a lot of memory being used, but the net result is it's working. This is drawing at a reasonably nice frame rate. And this is the demo here where we have, the panels are just randomly assigned colors. You can see in my panels, the missing corners, pixels, and things like this. I got some dinged up panels, but for these kind of testing, I don't care. I'm just trying to make sure that driver works. So that was that. This is all up the website at the driver. We did some measurement at it, and this was what threw me to what motivated me to talk to Chip yesterday. When I went to 6 panels live instead of 1, I had some really sluggish, really doggy code in there. And we went from 10 microseconds in one loop case down to 715 nanoseconds, just removing that. So dramatic improvements all over. So you can see now, as a 6-panel chain, we are now running, these panels are rated for 20 megahertz. I'm successfully running them at 28.6 megahertz at the current speed. This is bit banging. This is not using streamer or smart pin. Although Chip and I are continually discussing how we actually can do the data stream with smart pins. And so we are still going to play with that. I wanted to get this driver released to everybody first. So you can see the data clock is running at 28.6. In order to do that, I am clocking this guy at 335 megahertz. I run my P2 edges at 335, no heat problems, nothing. They just run nicely. And so I'm doing this so I can determine what the maximum rates of the panels are and see what I can do. What this means then is a single line is taking us, we're putting out an individual line of the 6-panel group across all 6 panels at roughly 69 kilohertz. So 69 kilohertz rate for painting lines on the panels. A single PWM frame, that's 1/16 of a video frame, is we're doing at 2.18 kilohertz or 457.8 microseconds for a full frame. That's the entire, all the pixels of the 6 panels lit. We do 16 frames, PWM frames, so we can get the colors in between red, green, and blue. So we can do yellows and whites and everything else. So we run a single frame runs at that. You'll notice I say 32 rows at 384 pixels across a row. That's because we actually send out the top row and the middle row and continue to descend down in pairs like this. We send out 2 rows at a time. So I'm clocking out 32 rows, but it's actually painting 64 rows. We're doing that with the top half of the panel driven by RGB1, 3 lines of color, and then RGB2, 3 lines of color drives the bottom half of the panel. This is typical for all of our panels so far. So that's how I'm doing that. I really have to measure this because there's a lot of random overheads that can happen as you're trying to paint frames. I am double buffered in the driver. It takes us about 33.3 microseconds to convert 24-bit color full screen buffer, 72 kbytes, into the 16 PWM frames. So technically we can do that. We can write the next PWM frame set while the existing PWM frame is being shown and have the next one ready to go. So the driver at the end of a PWM frame switches to the next one it's given. If it hasn't been given one yet, a PWM frame set, then it just repaints the current one. So at the end of every PWM frame set, it will look for another one and just paint that one instead of the first one it had. So it should be switching automatically. This is what we're seeing. This is a single PWM frame. And you see me going 0 to 31 on the address lines here. And you see me doing a line. And each one of these then is the 384 pixels. But we have the top half color and the bottom half color. So that's what we're seeing here. So RGB1, RGB2. This is the clock, the pixel clock, and this is the latch enable and the output enable for the panels. That's how that works. Then we go to a single PWM row, and now you're seeing me using one address value for one row. They go from 0 to 31. And here again, you're seeing RGB1 and RGB2, so top row and then middle row of the panel, the clock of the data, the latch and output enable are here, and then we switch addresses during the output enable period. And so that's how these panels work. And so here's what we're running. I wanted to show you this because we're actually calculating the line rate. It takes us this period right here, 715 nanoseconds, to pull in the next 2 lines from HubREM to CogREM. And so I'm pulling in the data and then streaming the data out and pulling in data, streaming out. So what this means is that this row plus the 17 divided by 2 will actually give us the actual row rate. And so that's what I'm doing down here with this math. So that's how we derive the actual row rates that you see right here. I just took the long one, the short one, added the 2 together and divided by 2, essentially. All of this code has been released last night as of version 090. It's going to become 1.00 once I get the multi-panels working for those that have to be configured. Configuring multiple panels in a chain, the 64 by 64 panels that we have today do not require configuration. The panels that do require configuration require me to on power up, send a serial stream out that and then latch it into the latches that runs configuration for the driver chips on the panels. And doing that for one panel is easy, that's working. Doing it for multiple panels in a chain turns out to be a bit problematic and a bit mysterious to everybody in the other processor worlds, like the Arduino world and things like that. They're all having problems with it. It's a mystery, and there's 2 or 3 guys that understand it. I've been following their code and chasing down that code, and I still don't have mine working. I have a couple more ideas, so I'm not done yet. But anyway, multi-panel for those that require configuration, not yet working. And we're now moving fast enough to 28 megahertz that I kind of overran these guys. And so I got to detune it for that panel. And so I have to put in a special code that adjusts the weight states for that. I haven't done that yet with this release. So you probably see a 9.1 come out that'll get this panel back on the air. In the end, when I get multi-panel support for these working, I'll bump this up to 1.0. So pretty much that's the news. The latest driver is now in the P2 OBEX as of today. And this is the code. And I'll keep updating this with notes of what's the latest news. And I'll publish this information to the P2 Cube thread today. And that's all I have for an update. Are there any questions?
I have something to say.
Okay, please.
what we should do is we can use the streamer to output those byte streams along and then use a smart pin to do the clock generation. But
Okay.
it would make a nice little quick byte for Ken to set up that would show, because what we could do is we could capture that with another cog streamer. We could capture all the activity and then show it in a logic analyzer display through debug, so that we could actually have like a little test bench. So, you know, with some little example code so that people could more easily, without having to visualize so much in their brain, they could actually try out, you know, they could write their own little streamer code and coordinate it with clocking smart pins and actually see the result captured on their display.
Oh, nice.
On their host machine, just to help out with development. Because when you can see what it's actually doing, it takes all the mystery out of it. Otherwise, if you just see a couple lines of code that starts up the streamer and then await XFI for, you know, wait for the streamer done, the action's completely not in the code. It's all in the streamer. So
Right.
we need some way to kind of visualize, actually capture what's going on with the pins. Then it takes the mystery out of it, and it's very easy to get a handle on. And we have the debug displays to do that. We just have to have a little thing that can capture some activity.
Right. And we don't have to, in that case, you don't have to run it at performance numbers. And you can run smaller amounts of data, so you can really practice developing good streamer technique.
Yeah, because if we get this thing working with the streamer, we're going to be able to place the clock at any phase relative to the data.
Yeah, that's perfect. It's going to be a lot of fun.
Yeah, it shouldn't take that long to get working, but we do need like a little test bench for that. And I can just make a program that runs in a cog that opens up a debug display and then maybe looks for some event and then just captures some data lines and then shows them.
Right.
You know, captures some pin inputs and shows them.
That's going to be fun to do. All right. Thank you. And that's my update for that.
Thanks,
Stephen.
Yes.
Stephen.
I can hear you.
Do you hear me? Okay. Minor question. When you having problem with the configuration of the chipsets, all the chipsets are hard to configure, or the first one in the chain is easy and the other ones are hard to configure because you can't be sure all the bits are passing through the chipsets to the next connector?
No, let me show you what I do. I have a logic analyzer, and yes, you're absolutely right. There are a number of reasons for why it's hard to configure. My latest problem is this, though. The 6126, FM6126A is being particularly problematic because it doesn't enable the output port until it's configured. And so when you have multiple panels in a chain, when you attach a logic analyzer to the input of the chain and the output of the chain, and you watch what signals are transferring, you'll see that until the first panel is configured, the second panel can't see data. And so in the end, I have to configure 1, configure 2, configure 3, configure 4. I think I'm going to have to do it that way. So that's my next experiment. What some of the coders were thinking was they could develop the entire chain for all the panels and send it out once and latch it. That doesn't seem to be solving anything. And so what it probably means is that I have to do multiple configuration passes until all the panels are configured. That's my current hypothesis. Got to prove it, though. Does that make sense?
Yes, because what Chip did said about using a streamer to snoop at the bus and look what the bits are passing through, you can use another streamer at the output of the next connector to see how the bits are reaching to the next chipset.
Oh,
So
yes, of course. Yes. Yeah, I'm a logic analyzer guy. So the first thing I did was throw a logic analyzer on both ends of the panel and watch what was happening. Yes, you could do the same thing with the streamers. And that's going to be that's going to be a lot of fun once we gain more experience doing that. The challenge is still getting the electrical hookup. So you're running connectors. You're doing level shifting, both in writing and then de-shifting and reading. And so you kind of have to worry about that aspect of it when you're using the streamers to instrument, since the Hub 75 is a 5-volt system, not 3.3. But the net result is, yeah, it's a lot of fun. It's also this chipset configuration, because the chips are manufactured overseas. They're a bit of a black magic, because the thing they don't configure, they don't describe in the data sheets, is the configuration sequencing. And so we learn by rumor, we learn by people reverse engineering, we learn by people, some documentation from some chipsets which are similar, are better documented. And so you can learn a little bit and then try and infer from the better documentation to what the other chipsets are doing. It's a blending effort for sure, and it's a research effort for sure over a lack of information on the net. So you're hunting and you're looking through people's code and you're looking through rumors. So, well, I got it working. What did you do to get it working? And then they try and explain it, and the explanations don't necessarily make sense. And so it's been fun. But I've been successful, so far. I just have to go a little bit further yet. I appreciate what you're saying, though. Thank you.
Okay, thank you. Thank you so much.
Thank you. Any other questions? I guess then we go to what's on people's minds.
Hey,
again, if that's what you want, unless you have something
Stephen,
else.
wait, I have a question.
Oh,
We were talking about yesterday how it scans out, it can scan all 6 panels at like 2 kilohertz, right?
yeah, my data rate, yeah.
Okay, but
My data
in
stream,
order to get, wait, what's that?
without my numbers in front of me, it's hard to confirm, but yes.
Okay, so anyway, that's how long it takes to update. But you said you have to do 16 of those cycles, over which time to get some variance in brightness.
To get variance,
colors.
to get variance in color, right? I'm doing PWM. And so what that means is that I basically, we take the 24-bit color and we map them into is red, green, or blue on or off in those 16 phases of the display. And so based on brightness, red may be on longer or it may be on shorter. And based on brightness, green is on longer or shorter of the 24-bit color value. And so we map that into the PWM. And so if you're really low intensity gray, for instance, you may be on for 1/16 of the period. And so we control brightness based on 16ths of the panel display rate.
That means then you're just shifting out R, G, and B bits per LED. Every LED has an R bit, G bit, and a blue bit.
Yes, that's the RGB1, RGB2 values. And so, yes, if I go back to sharing this screen,
it's going to take, so we're doing the, we're not sending brightness out, we're creating the brightness by rescanning.
Correct. And so what you see here is RGB1. This is 3-bit values. There's a red, a green, and a blue for RGB1, which is the top half of the panel. And RGB2 is the bottom half of the panel, the 16 rows there. And brightness, just on and off values for those 3 LEDs. So there are 3 LEDs, and each clock here, and too bad I don't have the other diagram, where you can actually see the clock pulses here of the 35 nanosecond data clock, 28 megahertz. We're clocking in those 6 values, RGB and RGB. We're clocking those in at 28 megahertz to the latches across the panels. And we're doing those for the 384 pixels across the entire 6-panel chain.
Right.
And then we hit this little latch enable and output enable thing in between.
So we're getting 4 bits per color, basically, then, if we do it 16 times.
Correct. Logically speaking, you're getting 40 bits, 4 bits per color. So we transformed the 24-bit into 4 to do this. And so, so that does give you some brightness, and it gives you, but without a lot more memory, you're not going to get a lot more resolution.
So are we only storing, let's see, when we output these bit patterns.
Shame on me, I'm wandering these panels while you're looking at it. Sorry about that.
No problem. I'm just thinking though, that how do we then cycle our data? What happens in the data domain between outputting to the panels? Because we have to like do some kind of like decrement with like stopping at 0. How do we get, as we rescan the panels, how do we realize the different intensities? I mean,
Okay,
I know that we're going off and on, but how do we translate a nibble into, you know, 1 of 16 or n of 16?
There's a when you commit, the way this driver works is you have a full screen buffer, which is 3 bytes for every pixel that there are on the 6 panels. So you're putting a 24-bit color in each pixel. When you say, I've got the screen buffer built and filled in the way I want it, I drew my rectangles, I drew my circles, I moved my animation right a notch or something, 1 pixel column, whatever you've done, and you're saying, I'm ready to commit this frame, then you call a commit. The commit routine actually translates the screen buffer to the PWM buffers. And so it then maps, it does, if we're using gamma correction, it does gamma correction. If you're using brightness limiting, it does brightness limiting. And then we take the resultant value and we map that then across the 16 PWM frames. And so based on this brightness, which frames are going to be enabled for this pixel in the red space and the green space and the blue space.
So you have to come up with basically 16 different groups of 384 patterns in order to realize the variance.
He's basically taking the original image and splitting it out into 16 separate single bit images,
right,
that equate to the PWM pattern to send for each pixel. Right?
So was that when we were playing with this yesterday, was that all happening in another cog in the background?
Yes, the driver is running its own cog, so it sits there and constantly paints the panels. And it's given a pointer to the PWM frame set. And so it will just iterate through the PWM frames over and over again until you give it another pointer. So imagine that you're doing an animation. I'm going to paint the static form of the animation, commit it to a frame set, and hand that frame set to the back end driver. Then I'm going to move things around and then commit the next one. The driver takes care of switching PWM frame sets at the frame set boundary. So now you can effectively do video without tearing and things like this, because we're double buffered PWM frame sets. And with the first cog, go ahead.
Sorry, you give some signal to say, okay, we've just used this data. We're going to start using the next data, so start redrawing on the invisible frame buffer the next thing. So as fast as we were going yesterday, we were not outpacing it.
No. We are, what we've done is we've made it less time to paint the complete PWM frame set because we're running so much faster. In the end, though, the time to commit the 24-bit screen buffer to calculate the 16 PWM frames, the single bit frames, is much faster than it takes to paint a single PWM frame, I believe, since it's all written in PASM, that we can actually achieve full frame rate animations because we're faster. It takes longer to paint the panel than it does to do the conversions.
I see. Okay, so we weren't outpacing it.
No. When that was written in spin, yes, we were easily outpacing it. But I rewrote it in PASM, and the conversion now to PWM frames is very quick.
Okay.
Now, when you get to the panels that Roy is using, and I have a copy here, where they are 1/8 scan, we're actually putting out twice the panel width as a row to achieve 4 rows of pixels being painted instead of 2 rows of pixels during the bit time. And so now we're putting out twice the width of the mechanical chain or the physical chain to do 1/8 scan, and we're painting 4 rows at a time. So the driver had to adapt to that too, and that requires a different PWM conversion from screen buffer to PWM buffer layout. And
Yeah.
so those 2 routines exist side by side, and we pick the one based on the panel you're using.
So do you do this by some kind of translation lookup, or are you like adding whatever the frame number is and then looking for an overflow in the carry and then using that to write the final bit into the bit buffer? How do you do that?
No, it's just a straight translation. And this is what I was doing for my measurement. If you remember a couple meetings ago,
This is
by
where
the
the
way,
gamma
this screen is showing you the clocks before Chip and I smoothed it. This was doing get along, transmit 4 bytes of the long, and then get along, transmit 4 bytes of long, get along, and you see how jerky that was. And that extent, and we went to a byte routine now where this is all linear, and so Chip helped me see that we could do that with much more effective clocking. And so this is a really tiny line here, but showing you what it looks like. That's what the diagram is showing you. Back to what I was saying. It's just linear math for calculating what goes into the PWM values. And so I'll take a 24-bit number and pull off the end ranges and then scale it. And that gives me a PWM result. And so I'll put a number 0 through 256, 0 through 16, 0 through 15. And
So you're ultimately using a lookup table.
it's math versus the lookup table. You don't have to do a lookup. It scales nicely. And I'm putting a value of 0 to 15 in the PWM buffer. And then the 0 to 15 is translated on the fly. I'm sorry, what do I want to say? What's recorded in the screen buffer is actually the PWM value in the end as you're assigning pixel colors to the PWM, to the screen buffer. And so I'll have a value of 0 to 16 for red, 0 to 16 for blue, and 0 to 16 for green. And then that value is linearly translated to the PWM buffers itself. And so what I was measuring was, with a value of 0 to 16, 0 to 15, am I getting that amount of light change in the value? And when I measured using the light sensors that I have, I literally am getting 1/16, 2/16, 3/16 of the brightness for each of the LEDs. And so,
that's with gamma correction and everything going on. That's all part of the process.
correct. And so I literally am getting really good values from the panels. I was expecting to see things a lot worse, but I am getting literally 16ths of brightness.
Yeah, it looks good. Yesterday, your whites looked really white. They didn't look blue or anything.
Yeah, they're pretty nice, but that's thanks to the panel manufacturers, not to corrections that I'm doing. I do see what the panel manufacturers have achieved. I can see the brightness differences in the red, green, and blue. But the panel chip manufacturers have tried to adapt their panels to be responsible with the output values. So they are corrected by the panels themselves in terms of brightness. Trying to see if there's any other useful displays here. No, but you can see what each of the different panel technologies we're doing. I'm going to have to update these now with the new algorithms because these clean up nicely. But this is still the older ones. So I think I actually say which, yeah, earlier version, different versions of the driver code. So yeah, it was how do I make sure I have the most performance possible? And so doing all the encoding earlier in time, so it's not last minute, really does save, and also saves on storage. And so by the time we get to PWM buffers, I have the red, green, and blue on and off values, RGB1 and RGB2 sitting in a single byte. And so the PWM frames are actually are a single byte per pixel, actually 2 pixels per byte by the time it's a PWM frame. And so that's how we're achieving both the data rates and the memory reduction. We can do 16 frames. I played with all the way out to 32 frames for PWM with a single panel. 32 PWM frames, 8 PWM frames, and I just settled on 16 because it was just easy and a natural transform. But I can really, the driver will handle my adjusting that frame rate. And so we could actually go to 8 PWM frames if we ran out of memory for larger panel sets, things like this, and play with it. So I'm just normalizing in 16 right now.
I see. Well, it seems to be working pretty well.
And yeah, in real life, the brightness, that's why the brightness throttling is going to be so easy to do, because we'll cap it and scale the values based on the brightness throttling. And now we can control how much power we're actually drawing from batteries when we do a battery version of the cube, just by setting a brightness threshold, and everything will automatically scale nice and sweetly.
But isn't it though that at the end you only have 16 opportunities to turn any given LED off or on?
Correct.
So how are we getting 16th steps if there's not inherent linearity in the light output?
There is actually inherent linearity.
Oh, because it's just raw duty cycle time.
Correct. So in the end, we really do have an inherent 16 steps of brightness. And when I'm doing brightness limiting, I'm just scaling. So I still achieve the 16 brightness steps with less power required, right?
I see.